Introduction and welcome to our presentation. I'm Yan, and this is my colleague Ray. We both are from the engineering team from Conviva. So today we are going to talk about one product we built at Conviva, the Auto Diagnostics Alerts, as called as Auto Alerts. So Auto Alerts is a system that is automatically detect anomalies along the video streaming pipeline and automatically diagnose the root cause so that the immediate actions can be taken to resolve the issue. So next we will go to the details of the product. So as just mentioned, so Auto Alerts, actually we deal with the issues in internet video streaming, but actually that's just a part of what we do at Conviva. From an engineering's point of view, we define Conviva as a data platform. So we monitor the video qualities, we define the KPIs, and we compute the KPIs both at real time with second-level delay and offline with delay of minutes. Also, we optimize the video quality. We have fairly sophisticated algorithms, both are running on the client side in the video players and on the backend side, which constantly improves the video quality. So for example, we try to reduce the waiting time before the video starts. We try to avoid buffering, and we try to recover the video from any CDN failure. So the ultimate goal behind all this work is to maximize the viewer engagement, which is the key to the success of our customers, so mainly the video publishers. Online video streaming, as called as OTT, is growing really fast these days. So in the past couple of years, we have seen dramatic shifts in the industry. So basically, many content publishers have put their contents online besides the traditional cable TV. And more than that, so many contents can only be viewed online. So based on a prediction by Cisco, by 2019, more than 80% of the global internet traffic will be for online video streaming. So as you can see, the industry is growing extremely fast. But it is still a very difficult work to guarantee a successful end-to-end streaming. So this graph just shows a very typical streaming pipeline. Actually, this is a simplified version because we didn't put the entities such as the DRM, the CMS, or the ad servers. So just a simplified version. But you can already see there are many entities along the path, and there are actually many paths on the pipeline. So the problem is, so any entity on the path can fail at any time silently, and no one knows because there's no end-to-end owner for the entire pipeline. And that can directly cause degradation of the viewing quality. Just to give you a very simple example. So, as shown here, the viewers can choose different devices to stream the video. And for example, the player for one device has a bug. Take iPhone as an example. And that bug can cause many viewers that are using iPhone suffer from long buffering. And you can see these are the high spikes in the buffering ratio. So this is just a very simple scenario because we know there's a single issue. The iPhone has an issue, then you can just go ahead and debug the player on iPhone and solve the issue. But actually, in more common scenarios, we will see issues happening on many multiple entities along the pipeline. So here's another scenario. So think about the scenario that people are watching a live event. So they can choose different devices to stream the video, the live event. They can use iPhone, they can use desktop, they can use Apple TV. And then the device can stream from multiple CDNs also. And then there's one live encoder in front of each CDN. It's possible that one live encoder can have an issue. And then that can cause one of the CDN stop receiving data from the origins. And then which eventually cause all the viewers that are streaming from that CDN fail the playback or suffers from high buffering. And in that case, as a content publisher, I probably will see many issues happening on many devices. Then how do I know what caused the issue? And how do I know which part I should fix? So without the answer, no effective actions can be taken. And the viewers will just keep suffering. But we don't want the viewers to suffer, and we need to fix the issues as soon as possible, because quality is really critical to engagement. So based on our survey, 1% increase in rebuffering ratio can cause up to 16 minutes less watching time, and 58% of churn risk in 2015. And those numbers will just keep increasing because the viewers' expectation just keep increasing. Then what can we do? So basically, we need a system that can, at near real time, can detect quality issues along the streaming pipeline. The system should be able to diagnose the root cause among all the entities along the pipeline. And we also want the system to give us more data to help us to troubleshoot. For example, we may want to get the list of viewers that are impacted by the issue. We may want to see the error code received by the player, and we may want to see the time series of the metric and understand if the issue is getting worse or not. So there are many asks, and Conviva, actually we have built such a system. It's called the auto diagnosis alerts. So this graph just gives you a very high-level idea about how the system works. So the high-level idea is the system will analyze the time series of each quality metric that we are interested in, and then detect anomalies by analyzing the time series and run a root cause analysis algorithm to figure out the root cause. So basically, the system will load all the video sessions at every minute and generate and group the sessions into different grouping. Here, a grouping just corresponds to an entity along the streaming pipeline. So for example, we can have a CDN grouping, which consists of multiple groups of sessions per CDN. We can have a device grouping, so where one group just represents a set of sessions using the same device. And also we can have combinations of those groupings, here CDN and the device combination. So the system will group all the sessions and then compute the QoE metric for each group. And then it will also need to combine the metrics computed at this current minute with the metrics computed in the previous minutes so that it can construct a time series. And then this time series per metric will be fed into our anomaly detection and the root cause analysis algorithm to generate alerts and figure out the root cause of the alerts. So all this computation is done on a Spark cluster at every minute. So this diagram just shows you the auto alert system at the infrastructure level. So the boxes at the top represent the video players. So we have sensors running in each individual player, which constantly measure the quality of the viewing experience. And all the measures are periodically sent to our backend. Then we have a real-time computation stack on our backend, which take all those heartbeats, all the measurements, and summarize them for each video session. And then the summarized data is stored in HDFS to be consumed by other applications. And then our alert system will just load all the sessions every minute from HDFS. And then it computes the time series per metric, per group, and then run the algorithm to generate alerts. The data, the output data, which are the alerts, the root cause, and the time series, will be stored in Phoenix. And then so that our external API can be called to pull out the data. And also the system will call the push API to push the alert to our customers. So next we are going to dive into the details of the algorithms. So, yeah.
Okay, so how do we detect anomalies? So anomaly is defined as a non-trivial spike in the time series of a quality metric. So in this example, we have a time series of a quality metric called buffering ratio. So we can see there are two spikes, a small one and a big one. Obviously, the big one should have more impact to the video quality. So how to capture these two spikes? First, we need to estimate a baseline based on the trending mean of the past historical data. And next, above the baseline, we compute a tolerance threshold, which is several standard deviations above the baseline. The quality metric is considered as normal under the tolerance threshold. And next, above the tolerance threshold, we compute the area of each spike to reflect the impact of the issue. So the area is an integration over the time dimension and the metric dimension. Both characterize the impact. For example, the spike can be small but last for a long time, so the impact is big. It could also be a short but high spike, still with big impact. Yeah. If area exceeds area threshold, we would consider the spike as an anomaly. So the area threshold is configurable by our customer. They can adjust it to either have more alerts or only capture the most serious ones. We dedicated this control to customer because whether a spike is an anomaly or not depends on our customer's definition of impact. So they set the criteria. For example, some customer may only think the high spike as the anomaly because the small one has trivial impact to their video quality, while others may want to capture both. As Yan already showed in previous slides, the problem can happen at any dimension or any combination of several dimensions in the pipeline. So if we only run the detection algorithm, we might end up with finding so many anomalies without identifying which one is the real root cause. For example, if iPhone has issue, it may affect all the CDNs it streams from. Like in this case, both group Alchemy iPhone and the Level 3 iPhone are affected. Although we detected anomalies in these two groups, we shouldn't blame them. Instead, we should blame the iPhone as the root cause. So the key idea for the diagnosis is that among all the groups detected having anomaly, we should only blame the group whose subgroups are all bad, like iPhone in this example. Other groups are just affected by it and shouldn't be blamed as root cause. So to find the root cause more systematically, first we need to construct a diagnosis graph like this, where each node represents a group, like iPhone and Alchemy iPhone. And the link indicates a parent-child relationship. A parent group like iPhone is split into multiple subgroups. This split means among all the video sessions played on iPhone, part of them stream CDN Alchemy, and part of them stream from CDN Level 3. So basically, the parent group iPhone is a union of all its subgroups. So this searching structure provides this basically provides a searching structure for the diagnosis algorithm. So after building this graph, next we need to run the same detection algorithm for all the groups defined in this graph to mark if each group has an anomaly or not. So the detection algorithm was already shown in previous slides, like the baseline area stuff. So after marking all these anomalies in this graph, we search from the top level to bottom in the graph. Whenever we find an anomaly, we recursively drill down to find the root cause of the issue. The search ends when we find a group whose subgroups are all bad. Like in this case, because all the groups all the subgroups of iPhone are bad, we return the iPhone as a root cause. this is another example. We first detect anomaly in all group at the top level, then recursively drill down to find anomaly in subgroup, iPhone and Akamai. Both point to their common subgroup, Akamai iPhone. In this case, we should blame group Akamai iPhone as a root cause because only one subgroup of Akamai and iPhone has issue. If Akamai is the root cause, then Akamai desktop should also be bad. It's here. So if the iPhone is a root cause, then level 3 iPhone should also be bad, which is not the case. So that's why we blame the Akamai iPhone as the root cause of the issue. So from these two examples, we can see the diagnosis result highly depends on the structure of the diagnosis graph. In real production setup, we have more dimensions and combinations to consider, so the searching structure is more complex with some pruning to boost performance. So one limitation in the diagnosis algorithm is that sometimes we are not sure whether a small group has an anomaly or not because the small group has too little traffic and a very spiky time series. But this matters to us because, for example, if the level 3 iPhone has problem, then we should blame the iPhone as a root cause instead of Akamai iPhone. So what we do is that we introduce a machine learning module to help estimate the performance for such small groups in each minute. The machine learning model is trained based on all the video sessions. And each minute, we feed in all the sessions from the small group. And then we give a prediction of the average performance for this group. Minute by minute, we get a time series for this small group, and then run the same detection algorithm as shown before to detect if there's an anomaly or not. Yeah. So this is a distributed version of the algorithm using Spark framework. First, we load, assume we have two executors. First, we load the video sessions from HDFS into each executor. Next, we compute the quality metric for each group defined in the diagnosis graph. This C1 iPhone AK means the group of video sessions that are from video publisher C1, played on device iPhone and streamed from CDN Akamai. So basically this step, we generate the time series for all the groups in the graph. And then next, we shuffle the groups based on their video publisher ID so that all the groups from the same video publisher goes to the same executor. Like in this case, the C1, all the groups from the video publisher C1 goes to the first executor and C2 goes to the second. And after this, we build a diagnosis graph for each video publisher in each executor and run the issue detection and the diagnosis algorithm, and then persist the root cause into our database. So the whole algorithm is wrapped into a simple map function with all the complicated logic wrapped inside, like build graph and issue detection and the diagnosis. Here are some performance numbers we get at each stage in the pipeline. So the job is fired per minute, and we can roughly finish in 45 seconds on average. Yeah. So this is a real production example that we successfully identified a CDN failure in the live traffic of level 3. So this blue line is a time series of the root cause group. And we can see there's a spike in the middle. And the yellow line is the time series of the rest of the traffic. And it's smooth without any spikes. And on this graph, we also show the traffic volume for the root cause group and the rest of the traffic to indicate the impact of the issue. So other than that, we also show a sample list of the sessions impacted by the issue so that customers can see the IP, CDN, device, viewer ID, stream URL, and some other attributes to help them debug the issue and take action. So in summary, okay. Right now we have pushed the whole product into production, and we have received a very positive feedback from our customers. Now we can support 25 video publishers, 2 million sessions per minute, and multiple metrics. So in the future, we need to come up with a more systematic way to evaluate the accuracy of the detection and the diagnosis algorithm. This is hard because whether spike is an anomaly or not depends on our customer's definition of impact. So we have to collect customers' feedback on each alert we fired. Other than that, we also need to try different detection and diagnosis algorithm, as well as tune the system to improve scalability and latency. Oh, we are hiring. Okay, thanks.
Any questions?
No questions.
I just had a question about the time series data and how you structured that data in Spark, seeing how sometimes that's continuous and dependent variables. So.
The time series, we only construct like 1 sample point per minute. So basically, we have a system to compute to summarize the session's data at every minute, and then every minute we just load all the sessions within that interval and generate 1 point along the time series, and then we kind of cache the previous metrics in previous minutes, and then we construct the time series. So this is only 1 point per minute along the time series. So it's not like continually, at a second level.
Okay, thank you.
Yeah.
Any other questions? Okay, thank you.
Thank you.